Also depends on the temperature. Intuitively, this makes sense because as you heat up a reaction, what do you expect?
More energy?
Yeah, you're adding more energy to it. And for example, we use the example just for example, we use the example of sugar dissolving in coffee, right? If you have cold coffee, what tends to happen to the sugar? It stays at the bottom, right? It doesn't really dissolve very well. And if you heat it up, it dissolves a lot easier, adding energy to allow for the solvation of the sugar crystals. So as you heat things up, generally they tend to go faster, right? So we know our rate law can be expressed as our familiar form for this is just for an arbitrary reaction, A goes to products. And this would be for any order reaction, that's what it would be. And so we mentioned that the temperature dependence for our experimental rate law, where is that contained? Right. Where do you think the temperature dependence shows up in this equation, right? So we know the rate of the reaction, that's just what we're measuring, right? That's what we're looking at. How does the temperature affect the rate of the reaction? So where do you think the temperature shows up or will show up? Or where did I say it'll show up? Right. For each experiment, had to be done at what? Constant? Yeah, a little k, right? So the rate constant is where we see the temperature dependence. So that's contained in the rate constant, or little k. So we would write that little k is a function of the temperature. All right, so our proportionality constant that we talked about is related to the temperature somehow. And if we think about for a first order reaction, right, where we're looking at the concentration versus time, remember our integrated rate law? It was a linear plot, right? K was what on the linear plot? Does anyone remember? It was the slope, right? So if you think about it, as you increase the temperature, the slope gets, or increase or decrease, the slope increases or decreases, which means that the reaction is happening faster because we're getting to a larger concentration faster or a smaller concentration faster. And so the increase in the temperature generally results in an increase in K and a larger rate of reaction. And this shows up in an equation that's called the Arrhenius equation. And you'll probably see me misspell this or spell it 20 different times throughout the semester. But this gives us a relationship between the rate constant and also the rate of reaction. So uppercase K, right? Because as we change or increase lowercase k, that directly affects the rate of the reaction from our experimental rate law. And what this looks like is we have lowercase k as a function of temperature. So that's what it means when we have parentheses in T. This is as a function of temperature is equal to some constant A times an exponential factor, e to the minus EA over RT. So capital A, this is what we call the frequency factor. The frequency factor tells us like how often are we approaching making a transition from the reactants to a products. It's related to shape of things, orientation. If we're looking at collisions, how often are things colliding with each other? We were talking earlier, mentioning what do the units mean. This is like the molarity, how does the volume, and how does that relate to the probability of undergoing a reaction? That's all contained in this nebulous constant A, right? So we're not worried a whole lot about exactly what A means. Conceptually, we can say, we'll talk about an example of what it means physically sometimes. But it's not something that we're really going to be that concerned with. Then we have EA. So has anyone seen EA before? E sub A? Yeah, this is called the activation energy. in the activation energy, does anyone remember what it was? Yeah, it's the minimum amount of energy you need to start the reaction, right? So this is kind of like the hurdle you have to get over for a reaction to happen. The minimum amount of energy you need to put in to then start the reaction. R, does anyone know what R is? Yeah, it's the ideal gas constant is what R is. So it's 8.314 joules per mole Kelvin. Right, this is the ideal gas constant. And then T is the temperature. And we'll talk a little bit in detail about, what are all these things together and how do they actually represent, how the rate changes. But these are all the different variables that we have, or sometimes constants, in our Arrhenius equation. And the way you can kind of think of this is that the exponential factor right there, that's kind of saying how many molecules or what fraction of the molecules actually have enough energy to overcome the activation energy and allow the reaction to proceed. And then A is like saying how often are they actually colliding in the right orientation, the right conformation to then allow for the reaction to happen. So it's kind of like how frequently do we approach that minimum energy, and then how likely are the molecules to have enough energy to overcome that. Okay, am I good to go on? Okay. So with the temperature and the rate, let's look at an example. So here we have two molecules. So this is a reaction between methyl isonitrile and acetonitrile, and they undergo a transition at room temperature, right? And so you form these two molecules and they look almost identical to each other, except here we have the nitrogen in between the two carbons, and here we have the carbon in between carbon and nitrogen, right? So we've switched places, the nitrogen and the carbon going between these. And this happens spontaneously and at room temperature. Does anyone know what these two molecules are called in relation to each other? Is anyone familiar? Yeah, they would be called isomers, right? Because they have the same chemical formula, right? The exact same elements, they just have different connectivity, right? So these are gonna be structural isomers. So these are called isomers. And we'll talk a lot more about isomers towards the end of this semester, but we're just thinking about it right now. And so between these two conformations, the one on the left has a +1 charge if you calculate the formal charge on nitrogen, and the carbon has a -1 charge. And the one on the right, we have no net charge on anything. So one of these is going to be energetically less or more favorable, but they can exchange between these two states. And so you can say, well, what's the actual physical mechanism for switching between these two? And how can we understand the different variables and constants in the Arrhenius equation using this example? And so here's what we would call a reaction coordinate of the transition between these two. As Lee mentioned, activation energy is the minimum energy that must be overcome to transform into the products. And we've talked a little bit about how we're going to use a lot of arbitrary reactions and stuff. We can talk about a specific chemical reaction going to the products, but here we're just going a structural change between two molecules. And we see that in the reactants, we usually have the isonitrile product on the left, and then it has to overcome this energy barrier, right? And what that means is as we approach this state right here, the maximum of what's defined as the activation energy, that means you're just at a very energetically unfavorable state, right? Like you can imagine that conformation where you have the carbon-nitrogen bond perpendicular to the CH3 on the left there. So this H3C and this, they're perpendicular to each other, right? That's very high in energy. And all I mean when I say high in energy is like that's unfavorable. Like the same way when you pull on a rubber band, you feel that force that wants to restore the rubber band. when the rubber band is not stretched, it's happy, right? It's at equilibrium. This molecule, when you twist it like that, it's like twisting, if you had a screw with a rubber band on it, and you twist it and it wants to spin back in the other direction. That's kind of what's going on here. And so that state is not very favorable. It's going to want to come down from there, right? So you're going to go to the products or the reactants. In this state we call, I don't have enough room there, this state is generally called the transition state. And so that's the state where we're high in energy, and about 50% of the time we're going to move towards the products, and about the other 50% of the time you're going to roll back to the reactants in this case. And so in this case, it's easy to see what a transition state is because it's just a conformation change. The molecule is just changing shape a little bit. This can also be in a chemical reaction, right? So you can think of the transition state, let's say between hydrogen gas and fluorine gas. The transition state potentially is where you have two molecules with each other and hydrogen atoms like in between the H2 and the F2. And so that's kind of like the transition state where it's bonded partially to both, but not fully bonded to either. And that's not a very favorable state for it to be on. It's a little easier to imagine it with physical examples like this rotation here than it is with a chemical reaction, but it's the same thing for chemical reactions as well. And so for this specific transformation, just to go over, review a little bit of the thermodynamics you guys have seen, it's energetically favorable, which means the products are downhill. And what would we call a reaction of that nature? When your products are lower in energy than the reactants? You remember? When we release energy into the surroundings, or we absorb energy into from the surroundings? Exothermic and endothermic, right? So when we have something that releases energy, or it goes lower, does anyone remember what that is? Exothermic, right? Because the excess energy goes out into the surroundings. So this is exothermic. And then it's endothermic when we take in energy from the surroundings, right? So this would be endothermic. And so these are related, these are related to thermodynamics rather than kinetics. So we'll talk more about this when we get into equilibrium, thermodynamics and equilibrium, because we didn't see the enthalpy or anything like that show up in our expression for the rate constant, right? We only had the activation energy and the temperature. Those are what affects how fast a reaction proceeds. Whether or not it's exothermic or endothermic, those don't affect how fast a reaction will happen. And so we can imagine then that the approach to this transition state is going to be related to the frequency factor in a way, right? So if this is our plot, bless you, energy, and then this is the reaction progress. Remember, it's exothermic, so we end up lower in energy. This kind of movement, right, where we start to rotate and the bond weakens, is the approach to the transition state. And a lot of times what you'll see is people will reference this point with like a equal sign with a line through it and a little star right there. That's usually how they identify the transition state. And that's at the top where the activation energy is. The thermodynamics are related to the enthalpy, right? And when we talk about equilibrium, we'll talk more about that. But the enthalpy, which is the absolute difference in energy between reactants and products. So equilibrium is going to be related to absolute energy differences, and kinetics are related to the size of this energy barrier that you have to overcome, the activation energy, which is why the Arrhenius equation doesn't have anything to do with whether it's exothermic or endothermic. In this frequency factor, which was A, we can think of that as with this specific example with the acetonitrile and the isonitrile, that every time the molecule starts to wiggle, that can be thought of as an approach to the activation energy, right? That transition state is when it's fully perpendicular. Every time you start to move like that, you start to approach that energetically unfavorable state. And so the frequency factor, in this case, physically represents, how often is it, they say wag here, but it can be a wiggle too, right? So it's how often is this molecule wiggling such that you're getting this transition. So this is as we approach the transition state. So if we look at the plot right here, you start to have a shape like this. This approach is related to the frequency factor. And so most of the time, the more complex states undergo the transition, meaning that they make it all the way to the products, right? The more kind of farther up the hill you get pushed, the more likely you are to make it to the products. To make it and again, here we have a physical process where you're just rotating two of the atoms in the molecule, but that can be represented as like a reaction, right? And so that's kind of how we interpret the frequency factor. The exponential factor is the number, so I mentioned this in lecture, we saw it a little bit with the integrated rate law. This exponential factor is usually a number between 0 and 1. That represents the thermal energy or the fraction of molecules that have enough energy to overcome the barrier. Of molecules greater than or equal to the activation energy. And so if we think about numbers between 0 and 1, you might think about probability, right? You can't have more than 100% chance for something to happen. So generally, this can also be thought about as the probability of a transition. And so this exponential factor depends on both the temperature. This is what we call the exponential factor. Depends on both the temperature and the activation energy of the reaction, right? So it's not one thing or another that's only important, and it's not the absolute value of one thing or another that's important. It's how do RT and EA compare to each other. That's the question that you're thinking about when you're looking at the probability of the transition. RT kind of represents the average thermal energy or kinetic energy of all the particles, and EA is a specific energy value that allows the transition to happen. So if we have a lot of thermal energy, like you heat something up, right, it's going to make it more likely for a reaction to happen, right? But if you have a lot of thermal energy, but the activation energy is even larger, then that means you haven't added enough energy to the reaction, right? So it matters how these two things compare with each other. And so one of the things I'll ask you guys is, okay, if this is our reaction, this is the temperature, and this is our activation energy, how does that affect the probability of the transition? And so we can usually look at independent cases of where one is large and one is small. So a low activation energy or a high temperature, right, relative to each other. So this means that EA is small or the temperature is high. We have something like E to the minus something small divided by something large, right? And if you have something small divided by something large, how will that number be? Small or large? Small, right? So that's going to be something E to the minus small. And if something's small, that means it's getting close to 0. That's another way of saying that. E to the 0 is equal to 1, right? So that means that our exponential factor, which goes between 0 and 1, right? If the temperature is large, that means that that probability goes up to almost 100%. Which means as we heat something up, the probability of that transitioning happening for the reaction is going up. It's approaching 100%. If we have a high activation energy or a low temperature, then that means that we have something like E to the minus large over small. And is that going to make what's in the exponent there large or small? Large, right? So that's going to be like E to the minus large. That's like saying it's approaching infinity, right? And as we decay and decay and decay, it approaches infinity. This is going to eventually approach 0, right? So if the activation energy is super large or we cool something down, that means the reaction should slow down to a halt, right? And how does that show up? Well, this is the exponential factor in the Arrhenius equation, which is in our rate law, right? So the rate of the reaction as K approaches 0 should approach 0, right? So if we think about the rate is equal to K, A to the M, which is equal to A, E to the minus E, A over RT, A. All I did was I just plugged in the Arrhenius equation to there. If that exponential factor goes to 0, then the rate of the reaction has to go to 0 too, right? Because 0 times anything is still going to be 0. Right, so we can use a little bit of intuition about what we know about the world around us to then relate that to then our experimental rate law expression for what this rate constant is. And that's where our temperature dependence is going to show up. Okay, so summarizing everything that we mentioned about the Arrhenius equation, the frequency factor, this was related to what? How often we approach the what? Or we think about our plot. Yeah, how often we approach where the activation energy is defined or the transition state, right? So this is how often we approach transition state. Then the exponential factor, this tells us, how do the temperature and activation energy compare to each other? This tells us the fraction of molecules that have enough energy to overcome, or it's related to that have enough thermal energy to overcome the activation energy. What fraction of molecules have more than EA energy? Right? We can approach the transition state as often as we want, but if we don't actually have enough energy to ever overcome that barrier, well, the reaction will never happen. And so how does this affect the rate of reaction? Well, we know that this is our experimental rate law for AA goes to products. And we can also rewrite this as AE to the minus EA over RT, A to the power of M, like that, right? So as we increase the temperature, right, that means that the exponential factor is approaching 1. That means that the rate is going to go up, right? As the exponential factor gets closer to 1, the rate of the reaction has to get faster, or that has to get larger. If the temperature goes down, or the activation energy is too large, this is approaching 0, and the rate of reaction goes down, right? An increase in lowercase k means an increase in uppercase k, and a decrease in lowercase k means a decrease in uppercase k. Rate constant, rate of reaction. So now the part that's relevant for the lab, I mean, all of this is technically relevant for the lab, but the part that's actually useful for you guys is we have our Arrhenius equation, which is related to the rate of the reaction. But how does this actually show up when we plot data, right? How can we actually use this in experiments? And so we can measure these different factors in the laboratory, so like the activation energy, that might be something you're interested in, or the frequency factor, we can measure this by using the Arrhenius equation. If we know what the rate constant is, does anyone have any idea how we might find the rate constant for a given temperature? Have we solved for any rate constants today?
We can create our little table.
Yeah, you can do the experiment changing the concentration, and that lets you find the order of the reaction and then the rate constant. Right, so you can find K, and then how would you can then find the temperature dependence by doing one of those experiments over again at a different temperature now. And now you'll have 2 different data points with different temperature. So it might not be obvious yet, but once you do the first part of the experiment, which you guys did last week, and then you change the temperature, you can then manipulate this equation to then see how we can solve for other things like the exponential factor or the activation energy of the equation. And so how do we do that? Well, if we want to isolate something that's in the exponent here, how are we going to do that? The logarithm, right? Whenever we want to pull something out of the exponent, we can take the natural log of both sides. So we can take ln of both sides. So we get ln k is equal to ln a e to the minus ea over rt. We can use some identities. We know that when you take the logarithm of e, right, what's going to happen to those two? Those will cancel out, right? Those will nullify each other. But we need to separate them first somehow. Well, if we have the logarithm, and remember I said this last week, of xy, that's equal to the logarithm of x plus the logarithm of y. We can separate them like that. So we get natural logarithm of k equals ln a plus ln e to the minus ea over rt. Move that up here. That gives us ln k, and sorry, this is lowercase k. This is the rate constant, equal to ln times the frequency factor minus ea over rt. You say, okay, well that looks kind of complicated. How does that help me at all if I only have 2 data points in an experiment? So remember earlier when we were talking about, well, anything looks like a line if you plot it a certain way, right? So what do you guys think will be our two variables here that we're looking at? Before we make sure that it looks like a line, what are the two things that we're changing in our experiments, right? The first thing we did is we solved for K, right, at different temperatures, right? So that's one thing we know is going to be changing, is the rate constant. Because we know when we change the temperature, that's what changes, right? Which means the independent variable has to be what? Right, if K is our like Y, right, how can we make this, before we even make it look like a line, K is a function of what? What is this, our discussion about the Arrhenius equation telling us? Right, why did we bring up the Arrhenius equation? What does it tell us? Huh? It tells us a little bit, the frequency factor is included in the Arrhenius equation, right? But what was the thing we were looking at? How, the rate constant depending on what? The activation energy, it will, but the activation energy is actually something that's inherent. That's just a molecular property. That means like that energy barrier is, unless you add a catalyst, is always going to be the same. Right? We were talking. Did someone say something? Eventually, we'll say all the variables in the equation, right? We were talking initially about the coffee, right? And what was the difference in the coffee and the sugar dissolving? The temperature, right? So the Arrhenius equation is giving us a relationship between K and the temperature. So we should say, okay, these are the two variables that we're kind of interested in. This is what we want to know, how these two things are related to each other. So if I rearrange the equation to look something like this, EA over R times 1 over T plus ln A. So all I did was I just moved stuff around, right? We know that we're relating the rate constant and the temperature. Does anyone have an idea of what two things we could plot next to each other to then find something like the activation energy or the frequency factor? Or maybe if I look at this, how could this potentially look like a line? Right, what would our Y variable be here? It would be ln K, right? So this whole thing is like Y, right? And what's the equation for a line? mx plus b, right? So we have mx plus b. So minus EA over the ideal gas constant. That's our slope. 1 over the temperature. That's our x value. And ln, the frequency factor, is our y-intercept here. So that means if we plot the natural logarithm of k versus 1 over the temperature, then we should get a line where the slope is the activation energy divided by the ideal gas constant, and the frequency factor is the y-intercept. And so you say, okay, well that sounds kind of weird. So what I'm saying is that if we have, I'll go back to that in a second. If we have a plot, and if I don't go back, remind me. If we have a plot, our x-axis is going to be 1 over the temperature. Our y-axis is going to be the natural logarithm of the rate constant. And we're going to have some line that goes through like that. In this equation of this line is going to be like ln k equals minus EA over R, 1 over temperature, plus the natural logarithm of the frequency factor. And so if we have a plot, or if we have data, we have a series of data, we have the rate constant, as a function of temperature, meaning we've solved for the rate constant at each temperature, and then the temperature, we plot that versus the different temperatures that we've measured it at, and we could just plot them together like this. We plot, if we, let's say our natural logarithm value was, our rate constant value was 2, we would plot natural log of 2, that's our y value, versus the temperature was 300 Kelvin. That data point would be natural log of 2, comma, or 1 over 300 would be our x value there. And so we'll do more of the plotting in the next lab, but for this lab it's still relevant because you're technically still doing the same thing. You're just not doing a series of data. You're looking at 2 data points, right? Because you only did 2 different temperatures for one experiment, right? So I'll go back to this while I ask you guys this. If you have just 2 data points that you're comparing with each other, how did we deal with that before when we wanted to solve for one thing in that equation? Related when we were looking at the rates of the reaction. That's what we started off doing today in lecture. Right, when you had multiple experiments, what did you do? How did you compare them to each other if you wanted to actually mathematically solve? You took the ratio of the experiments, right? So what we can do is we can take the ratio to experiments at different temperatures and then we can, if we don't know the rate of the rate constant of the new equation, we can then use that to solve for one or the other, right? So we have temperature 2 and temperature 1. We have the Arrhenius equation for temperature 2 equal to A e to the minus EA over R T2. Divide that by K1 is equal to, and these are lowercase k because these are the rate constants. A e to the minus EA R T1. And so the reason we don't put any subscript for EA is because that's inherent to whatever the molecule or the reaction that's happening, right? So that activation energy is the same as when something's exothermic or endothermic. That's just an inherent property of the reaction. The only thing that's different between these experiments is the rate constant, which we know because we only know one of them, but we know that that depends on the temperature, and the temperature at which we did the reaction. The frequency factor, that's just related to the probability. So if conditions are identical, the probability of them approaching the transition state, right? So that's gonna cancel out. The same way when we took the ratio, the rate constant canceled out. Frequency factor, rate constant are kind of similar in that sense if it's at constant temperature. And then we can take the ln of both sides. After simplifying this, because this is going to be e to the minus EA over RT2 minus EA over RT1. Right, so the same way when we had the addition of exponents was related to the multiplication of 2 things that had powers with the same base. If we had something like A over x to the y, that's equal to A to the x minus y. That's just the identity. So I just did the same thing. I subtracted them from each other. So we get K2 over K1 is equal EA over R 1 over T2 minus 1 over T1. Right, so activation energy is the same, so I can pull it out of the expression up there, and R is the same. Ideal gas constant is just a constant, activation energy is a constant. So I can pull those out, and then now I can take the logarithm. This is not a negative sign. The logarithm of both sides. ln ln. What happens when we take the logarithm of the exponential? Like ln e here, what happens to that? Cancels out. Those are the inverse operations of each other. And then I'm going to go on to the last step here. Good. Go back. Let's finish writing. Good. So when I do that, now I have ln k2 over k1 is equal to minus ea over r 1 over t2 minus 1 over t1. Rearranging everything, we get ea is equal to r ln k2 over k1, all divided by 1 over t2 minus 1 over t1. And this should always give you a positive number, right? Because activation energy is always going to be a positive quantity. And so that, when you're in lab today, is how you're going to use the Arrhenius equation to then solve for the activation energy. You're going to have measured the rate constant for two different temperatures. The rate constant is similar to what we've been doing in lecture. And then you're going to use the Arrhenius equation to then solve for the activation energy. Okay. And so we're not going to go over any examples of this in lecture. I mean, in lab, we'll have plenty of time to do that in lecture. We're going to kind of figure this out as we go when you try and do your calculations for your lab today. So I'm going to end this right here. I'm going to leave